Okay, okay.
And click that hide option, right? Stop sharing and hide. Click that. Otherwise, it would be recorded in the session. All of you able to see the
Okay,
screen?
hello everyone. Hope you all are doing well. May I start?
Yeah, yeah, yeah.
Okay. So hello everyone. I'm Arshpreet Singh. I'm one of the co-organizers of Kaggle Days Meetup Delhi NCR. I welcome you all to the first webinar of a series we just launched, Data Ketchup. Our first meetup is in collaboration with DSC JIIT Noida. I'm also a part of that. DSC, it's the Google Developers Program for university students. You all must be knowing that. And at DSC JIT Noida, we conduct several workshops and sessions throughout the year. Like we conducted DevFest,
Arshpreet,
GCC,
your voice is
Task
not
Force,
audible.
Explore ML sessions, and etc.
Arshpreet, your voice is not audible.
Arshpreet,
Um,
just 1 minute. All those who don't have Arshpreet's
okay.
voice inaudible can just write a +1 in your message box
Like in the chat window.
in the chat. Yeah.
Oh, it's all a hell lot. It's a hell lot.
Okay, so I guess either Ion or me should take over from here. Ion, will you take over?
Okay.
Yeah, 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 sure. I will do that.
Yeah.
Uh,
Okay.
so,
Arshpreet, I hope it's not a problem.
Let me try once again. If
yeah, yeah, yeah.
is it's audible, then I can start. And if it isn't, then Ayon can continue.
Okay, sure.
Okay.
Is it any better now?
All up to audience.
Yes, yes. Only audience can tell that.
yeah, yeah, yeah. Perfect, perfect. Go ahead. Go ahead, Arshpreet.
Okay, okay. So here's the agenda for today. First, I'll be telling you about this initiative, and then I'll introduce you to our community. And then from 12:15, our speaker Souradip Chakraborty will be telling us about Bayesian linear regression. And then after that, we'll have the Q&A session where Souradip will answer all your questions. Um, I guess the voice is better now and it's
Yeah, yeah,
audible,
yeah.
right?
Again, slow.
Okay. I cannot even see the chat window because I'm presenting. So let me know.
To all those for whom the voice is not audible, guys, could you please use your earphones? Because are telling that it's audible using earphones. Preet, you may continue now.
Okay, cool. So what is Data Ketchup? Data Ketchup is the new series of webinar that our community started. It's a beginner-friendly series for all the data science enthusiasts. And who is it for? People who want to get started with machine learning and data science, and just anyone who wants to learn new things. Now, let me introduce you to the speaker for today, Souradip Chakraborty. He's a data scientist at Walmart Labs, and he's also learning. And to ask questions from him, you can comment in the chat during the Q&A session. And if any questions remain unanswered, you can just ask them later on the Telegram group. And as many of you must be new to this community, so let me first tell you about Kaggle Days Meetup. So what is Kaggle Days Meetup Delhi NCR? It's a series of events in Delhi NCR which aim to gather Kagglers and all those people interested in machine learning, artificial intelligence, and data science. And also, our community has people ranging from college students to senior industry professionals. Who are we? We are less of this. and more of this. Like we believe more in networking and interaction and learning from each other. And to tell you, there are more than 50 editions of Kaggle Days meetups all over the world, spread through 28 countries. We are India's first Kaggle Days meetup community. And Ayan Roy is the guy behind all this who brought this community to India. I guess it was back in June 2019. So now the point comes, why should you join Kaggle Days Meetup Delhi NCR? So here it is. You get to meet Kaggle enthusiasts from your city and interact with masters and grandmasters, share knowledge with local data science communities. And then we have meetups with different difficulty levels. Like we conduct professional meetups where only professionals are allowed. And yeah, it's absolutely free. The goal with which we started, learn how to get started on Kaggle. You get to network with people. Like I said, you get to interact with uh, Kaggle masters and grandmasters. And also, as this is a webinar, so people are missing out all the fun we have during our physical meetups, all the networking and all. So who can attend these meetups? This is for anyone and everyone who's interested in data science or machine learning, or is interested in participating in competitions on Kaggle. What we have achieved as a community. We have a very active group on Telegram with more than 1350 members, and the numbers are increasing rapidly. I guess it would be more than 1400 by now. Also, all the updates about our meetups and everything comes first on our group, so make sure you join it. Also, we have a whopping impression of 98,000 plus in 28 days on Twitter. We have more than 4,000 subscribers for our monthly newsletter. Also, we have conducted meetups in 11 months, out of which the last three were virtual meetups. We also supported 6 hackathons, 2 tech conferences, 1 Google Dev Fest, and 1 Google Explore ML session. Who made it possible? It's you guys who made it possible. All the enthusiasts who reached out to us, from students to working professionals. It's your response that motivates us to keep moving forward and keep growing this community. And yes, we're turning one. We're turning one in June next month. We are celebrating our first anniversary, or call it communiversary. We're gonna be having 4 meetups in the month of June. And as you can see our lineup, we have experts and grandmasters here. On top, you can see Grandmaster Abhishek Thakur. He's the world's first four into Grandmaster. So yeah, you can register for these meetups at this link here. Also, you'll have to register for all the 4 meetups separately. So make sure you do that. Yeah, so here are some pictures from our previous meetup. I guess this was the first ever Kaggle Days meetup in India. It was held at Grofers, Gurgaon. And then the second one at Tokopedia, Atlin. Fourth meetup at Internshala, Innovator. And then we had this professionals only meetup at Gardner. This is our sixth meetup. And this was our last physical meetup at Tokopedia. And it was really a grand one because you can see Grandmaster Abhishek Thakur was with us. And yeah, even after this pandemic started, we did not stop conducting our meetups. We conducted 3 virtual meetups in the month of March, April, and May. We would like to thank all of these organizations for being our helping hands. Now, let me introduce you to our family, our team, all the fellow co organizers Mohini, Tanisha, Arshita, Harsh, Vishal, me, Arshpreet, Prajit Mukherjee, Ishan, Bhartendu, Soumya, Somadas, and Ritesh. And most of us here are college students. Only Somadas is the one having a work experience. Yeah, so most importantly, in this time, you should stay at home, stay safe. These are all the precautions you should take. Wash your hands frequently, maintain social distancing, avoid touching eyes, nose, and mouth, all of that. And also, it's really important to take care of your mental health because it is as much crucial as your physical health. Um, I've seen people getting anxious and depressed that they're not able to do anything during this lockdown. Maybe because they're seeing people doing all kinds of stuff. Like, see, we're in a pandemic. It's not a competition like who does more courses and more internships. Also, all of these certificates which people keep on posting on LinkedIn, they have no value if the person is not applying that knowledge and making good projects using that knowledge. So yeah, if you're getting motivated by what others are doing, then it's great. But otherwise, you just keep your calm and work at your own pace. It's absolutely okay to not do anything on some days and not being productive. It's okay for some days. So just take care of yourself and your family.
Yeah, interrupt. Sorry to interrupt, Ashpreet. Sashank, if your video stream is not turned off,
Yeah.
you will be removed from the meeting. Sashank Shekhar. Anyone's video stream, if it's on, our volunteers are constantly monitoring, you will be removed. Thank you. Ashpreet, you can continue.
Yeah, so these are the QR codes. You can scan them for registering for our, sorry, anniversary meetups. And you can also follow us on Twitter and join our Telegram group. And if there's anything you want to tell us or any kind of feedback, you can just fill this form at this link and we'll we'll take care of that. So yeah, I'll just leave the slide here till the speaker starts so everyone can register and all of that.
It's 167. Do you have anything? All of you, please switch off your video streams as well as audio streams. Souradip, yeah, you can just
Yes.
share your screen.
Hi. So,
So I'll just presenting then.
Yeah.
should I share my screen?
Yeah, sure. Pradeep, could you please stop sharing your video? Like all of you who are sharing their videos or have their audios unmuted, they will be removed.
All the attendees, please switch off your web streams. You will be removed from the webinar.
Yeah, Souradip bhaiya, you can start.
Yeah. So it is visible, right? Is it visible?
Yes, yes, it's visible.
Yeah. So Just to introduce myself, I'm Souradip Chakraborty. So this is the Medium link. So I'm writing an article on this one, on the entire talk and on this entire day. So it's most convenient for people because many times we have to share presentations, and because if we have to give a lot of picture, the size of the PPT increases. So I think Medium is a better link. So I'll post it recently after this session is done, and I'll share the link, and also I have the notebook with me. So probably that will be useful. Now, just to introduce myself, I'm Souradip Chakraborty. I'm currently working in Walmart Labs as a data scientist now, almost for 2 years, 2.5 years to be specific. And uh, so I have done my master's from ISI, Indian Statistical Institute, and bachelor's from Jadavpur University. And currently, I am also a Google developer expert in ML. So if you have to find out anything, this is my personal website. You go here and you can find the details about me. Yes. So today's session is primarily, so this is a data catch-up session on Bayesian linear regression and logistic regression, but I feel that logistic regression, it won't be possible to cover today. So mainly we'll focus on Bayesian linear regression. Now, what is the main purpose? So when I heard about the participants, and when I heard about that who all will be attending, so I got an overview that there will be people from different fields with different knowledge and different backgrounds also. So it is very important to understand certain basic concepts, and that's why I have chosen this topic. I feel that Bayesian was one of the most powerful topic, and is one of the most powerful topics of this in this current domain of AI and ML. And nowadays it has actually it has been a huge surge and a huge increase in its demand for Bayesian. So why is that? So the main reason is, if you are aware of the current deep learning methodologies and models that are currently going on, so it is like a lot of complex models are being built. For example, if we take about NLP, natural language processing domain, so the models are like BERT, which is a basically an attention based transformer, and it has a huge number of parameters. Now what happens is, when you apply this to business, if you give point estimates, or if you give just the value of the weight matrices, it is not enough for business. The business wants to understand that why the predictions are happening, why the weights are like that, which particular data point is causing it to be. So there is a lot of work that is happening from the interpretability side, because if we don't have interpretable models, it is of no use. And that is one of the main reasons that now people are shifting also towards Bayesian. And initially what used to happen is Bayesian, so there are a lot of ensemble models. For example, there is boosting, there is bagging based models. In boosting, there is light GV. So all these models are very good in giving very high accuracy, and in Kaggle and in different competitions, if we have participated, this type of models are like a super performer. So in such cases, Bayesian might not be the best to do, but after all, we have to implement it somewhere in a business use case, right? So the business persons and the managers needs to understand, needs to have an interpretable system. So for that interpretability aspect, the Bayesian plays a huge role. Now, so now, as I said, that one of the main focus is on now currently on deep learning interpretability with the advent of complex models. So because more is the complexity of the model, more number of parameters you are becoming, like it is becoming a black box like you. And in many places like banks, like financial institutes, hello, is it audible?
Yeah, you're audible.
Ganesh, you are requested to switch off your audio stream.
Yes. So, so in various use cases and scenarios, for example, in banks, in different financial institutes, in oil and gas sectors, so it is very critical sectors, and their interpretability plays a huge part. So at that, on those scenarios, this kind of, there are other interpretability measures also. Like in NLP, we use visualizing the attention models, visualizing the. So there is another thing called LIME. Then there is another thing called. So we have a lot of other interpretability measure, but Bayesian estimates are very robust, and they give you a complete full information about the coefficients, model coefficients, or weight matrices, or whatever you can call. So now, so this will be currently, so this is one of my parallel fields of research that I'll be delving into. So that is Bayesian and deep learning, and this zone of Bayesian. So this is probably the first first part of this, that we have to understand. So before going into Bayesian deep learning, we have to understand that what are the implications and how Bayesian can be efficiently implemented in linear regression, because that is the primary thing from which every model has started. So we have to be very aware of the mathematics going inside it, because let's say we as a data scientist or as a data science enthusiast, if we are not being able to explain the mathematical aspects, then it will be very bad for people who are not the domain experts. so I think if we need to understand the mathematics for sure, and so that is what my objective of this session will be. I will try to go uh, as much possible into depth of this Bayesian linear regression, so that everybody now after this session can just go into any article, any paper on Bayesian regression or further advanced concepts, and at least can have a ground level understanding. So that is the objective. So while researching for this session and then preparing the content, I found out that there are very less materials on Bayesian. So there are like few blogs, few articles, few paper, like a lot of papers, but few articles. So it's not like you will get a very interpretable certain write-up. So it is very important to be, so you will like, I'll request you to listen to this video carefully, because there are very less materials and it is a very complex concept to start off with. So now before, like, just to start off this session with the topic, before that we'll have to know certain things. So in linear regression we use a maximum likelihood estimate. So so maximum I came with this assumption that at least people will have some basic knowledge on how MLE or maximum likelihood estimate works for linear regression models. So if even if it is not there, I'll just give a very brief overview of how MLE works, okay, in linear regression scenario. So just to give an introduction, in linear regression is basically where it's like a model in the terms of y equals to W transpose X plus epsilon. So or if linear algebra is very uncomfortable for you, you can think it's like simple y equals to ax1 plus bx2 plus c plus epsilon, where c is the intercept and a and b are the slopes or the rate of change of the variables with respect to the response or the y. Okay, so now let's come to the MLE part. So if you can see in this MLE part, so all the links from which I have taken these pictures, or if I have written something, everything is mentioned. So you can just click and you'll get the full link. So now let's say if we think of the MLE for the linear regression part, so what happens is here, if you can see yi, so yi follows normal distribution W transpose xi and sigma square. So this is the primary assumption of linear regression. So yi is a random variable which follows normal distribution, where the mean is W transpose xi, or you can think of like ax1 plus bx2 plus c, and the variance is sigma square. So every random variable.
Hello,
Yes.
Bea. I'm
Yes.
sorry to interrupt. Can you
Hmm.
give some knowledge about what is MLE and
Yes.
what exactly it is?
Sure. So okay, so I think so I had one assumption that maximum likelihood estimation is known to you, but I'll just give you a very brief intuition to what happens. So what happens is, so if we have, let's say, if we have a sample of variables and it follows some distribution, let's say, then what we do is, now we want to find out the uh, parameters. Let's say, for example, if there is a normal distribution, then there are two common parameters, which is mu and sigma. So we want to find out the parameters mu and sigma. Now you have a sample and you have a distribution, but you don't know that what is the mean and sigma. So in such cases where you have to estimate the mean and variance of the distribution, in such case, for example, or in general any case, you can, for estimation problems, when you have a distribution but you don't know its parameters, we can use maximum likelihood estimate. So what is maximum likelihood estimate? You can just go and search in Google. You will get enough good materials like this. So for example, if you can take any blog like this, and you will understand that what happens. So for example, so in this case, maximum likelihood estimate, what it does is it actually maximizes the likelihood that those points are occurring, and accordingly it finds those parameters. So for example, if there are 10 points, let's say x1, x2, x10, so and we have a normal distribution, we know that that these points have come from a normal distribution now with mu and sigma. So we find out the best mu and sigma from given, which can generate this 10 data points, right? So that is the intuition or idea of maximum likelihood. And how you do it is pretty simple. You find out any distribution. This is the distribution, let's say, and you put all these values. So you put the values of x, and then you try to maximize the likelihood by differentiating with respect to mu and sigma, right? That is what we do normally. So yes. Yeah, okay. So I'll just see the chat also parallelly so that I can slow down a little bit. Okay. Okay, fine. So what happens is, let's say you have a uh, distribution. Let's say you have a probability distribution which is a normal distribution. Let me go to my blog. Yeah, let's say you have a normal distribution which is of this form. Okay, so you have a normal distribution. I'll just show you something. Okay, yeah, let's say this is the typical form of a normal distribution. Okay, so there are mean, mu, and here I have represented the variance 1 by sigma square as t. So you can like take whatever it is, but let's say this is the precision. So there are two parameters, mu and sigma square or t. Now what you do is you try, and this is the likelihood function. Okay, this is the PDF. So if you put the values f of x1 or f of x2 or f of x3, you will get based on, so we will replace x with x1, x2, x3, right? And then you will get the likelihoods of those points. And then what you do is you take the product of those likelihoods, given that those points are independent. So uh, as we know, right, that p of x1, x2, x3 can be written as the product of px1 into px2 into px3 if x1, x2, x3 are independent. So we take this product, and then what you do is you do now if you think like that let's say t is known and x1, x2 values you put, so the only variable is mu. So what you do is you take the product and then you differentiate with respect to mu to 0 to get the maximum value of those. So basically the intuition is, what you are doing is you are getting the maximum value which the best value which can actually maximize the probability of occurrence or the likelihood of occurrence of those data points, right? That is what MLE does. So it's clear. Is there any question? I'll just see my chat window there. Yes.
So basically,
Yes.
what you're trying to do is, suppose we have a normal distribution, so we are trying to find the peak point of the normal distribution using this.
So what we are trying to do is, so the normal distribution will have two parameters, right? Mu and sigma. Now let's say for the time being that sigma is known and we have to estimate mu, right? So now what we do is like now let's say somebody has given us some 100 data points. Okay, that this is my data point. I want to find out that it comes from which distribution, right? Now what I do is I have a normal distribution function. I know the PDF of normal distribution, and I know that, okay, these are the 100 data points that is given to me. What I have to do is I have to find the value of the best mu, which for which the likelihood of generating this data points will be maximum. So I have to find the best mean for which the generation of this data points is most probable, right? So what I do is, as I explained, then I go with this process. Is it clear?
Yeah, it's clear.
Okay, cool. So I think, Oyon, what you can do is you can just see the questions and maybe you can ask on the behalf so that because I won't be going to the chat screen frequently. So that will be fine, right?
Like I will just collect all the questions and send it to you over WhatsApp. You can just see accordingly, right? Or like if the webinar ends, you can answer them at a later stage also. We will share the doc with question and answer later also.
Okay, okay, fine. Okay, because there are a lot of things that needs to be covered, and yeah.
Yeah, sure.
Perfect. So so MLE part is, I guess, clear. So now what happens is, so now I am now writing the MLE for a linear regression. So in a linear regression scenario, so I think that people have tried out linear regression from using the sklearn package, which is the most one of the most famous packages. So if we use sklearn packages, so they will so there is an OLS estimate that you will get, that is the ordinary least square estimate. But there is another way of looking at the regression problem, and that is a very interesting way to look at this problem. So we know, right, that in a regression scenario it is y equals to a plus bx form, right? So I'll write it down here only. So we know that the regression equation will be in the form of y equals to a plus bx, right? That is how a regression equation looks like, plus some error. Now we know that this error follows a normal distribution with, let's say, with mean 0 and variance, let's say sigma square. Okay, so this is how a typical regression equation looks like, where error follows normal distribution with mean 0 and variance sigma square, and y equals to this. Now we can consider that y also follows normal distribution, since x is not stochastic. So follows normal distribution whose mean is a plus bx and variance is sigma square. Now, so this is what the regression equation looks like, right? This is what basically we will have to solve, or we will have to estimate. Now, if you see that the MLE, so if you see this equation, so it is a bit in terms of a like linear algebra, so it might be a bit complex for many of you, but I will say that this is doing the same thing. This is W transpose X comma sigma square indicates the same thing which I have written, which is a normal distribution with a plus bx and sigma square, right? So this is how. So now you know that we assume that xi's are independent, so each data point is not dependent on the other data point, for at least for linear regression. So now what we can break it into is, we can, so this is the likelihood, and we can write the likelihood as, if you can see, so it is likelihood of y1 y2 yn given x1 x2 x3 and xn and the parameters, right? So we can write this in the form of a product, because we know that y1 depends on only x1 and y1 does not depend on x2 x3 xn or something else. So y1 depends on x1 and y2 depends on x2. So practically we can break this probability of y1 y2 yn given this into probability of y1 given x1 into y2 given x2, and like that. So this is what is being done in this step. Okay, I will try to explain each and every step. So if you have any questions, just ask, or maybe Oyon can ask on their behalf. Yeah. So this is the way it works. So I am breaking this y1 y2, this joint, into individual. So y1 given x1 into y2 given x2, and obviously theta is the parameter. So for example, this entire so what happens in vector algebra, what we do is we write theta equals to, will be in this case, so it will be a vector a b c with whichever parameters we have, and it will be a vector, and we can write as a vector notation, but you can think, right, given a comma b comma c, like that. Okay, it is the same thing. So now once we know that probability of y1 given x1, so it follows a normal distribution, right? That is written here, that I have written that y follows normal a plus bx sigma square. And I have shown you that what is the typical PDF of a normal distribution. It is simple, 1 by root over 2 pi sigma square into this expression. Okay, because in this case the PDF is with respect to y, so here yi has come, and the mean of yi is, if you can see, this is the mean and this is the variance. So the mean of yi is, for example, for y1 the mean will be a plus bx1, for y2 it will be a plus bx2, like that. So this is the mean, this is the variance, and this is the expression for the PDF, and this is over 1 to n. It is basically, we are taking the product. Okay, so now what we do is, this is our likelihood. So once you have understood this part, so likelihood part is almost clear to you. So now what we do is, so that I have not shown here, because yeah, so that I have not shown. So what we do is, this is the likelihood and this is the expression, and if we take sigma square as constant, let's say, then what we do is we differentiate this likelihood with respect to, so I'll write here, so we differentiate this likelihood, we take the logarithm, because as you know, right, if this is in a product form and we take a logarithm, it will be a summation, simple summation. So now what happens is, now what we do is we take differentiate the likelihood with respect to, let's say, in our case it will be, since our parameter is a and b, so let's say with respect to a, and we make it to 0, and we take the double differentiation also and see that it is negative or not, because that will ensure that we are reaching our maxima, right? So dl dA equals to 0 will give you the estimate of a that is the most suitable for our data set, right? Clear? Yes. But now if you have seen this, so one of the most important point to understand is that MLE gives you a point estimate of the parameter by maximizing the likelihood, right? So I think somebody had asked the question that is it a point estimate or not, and yeah, it is a point estimate. So so just to give you a very basic overview of a point estimate, you can think like a point estimate simply is a value. Okay, it's a mean value, or you can think it as a value. So there is no distribution associated with it. So for example, when I'm estimating this, when I'm doing dl dA equals to 0, and I'm finding the value of a, so at that time I am not, I'm just finding the value of a. So a will have a single value. A will not have a distribution. You won't be able to know the variance of a, how the values of a are varying. You won't be able to know. You will just know the best value of a. Okay. So now that is one problem, right? You can understand that that is one problem of MLE, because you will know like an estimate, a point estimates, and that is not enough. And as I said that uh, with more and more focus on interpretability, people want to know the distribution, people want to know more about the parameter space, which is definitely not enough if we go about this likelihood formation. So in this case, what we do is we go for, now there is another estimate, which is a map estimate, which is maximum a priori, maximum a posteriori, sorry, maximum as posteriori. The links are given, you can check. I will not go into now this. I will tell you once I have explained Bayesian. Yes. So I guess till now it is good. So I'm moving to the next part. So as I said, that this model don't give you enough information about the distribution of the coefficient, whereas in Bayesian, we estimate the posterior distribution of the parameters. Right now, so okay, now like I assume that you guys know Bayes theorem, right? At least that is what the assumption is, that you are aware of how Bayes theorem is and how it is works, and probability, a little bit of probability understanding. So if you see, say what is the, I'll tell you in this particular equation, I will tell you which one is the prior, which one is the posterior, and which one is the likelihood. So here first I'll tell you which are the parameters. Here theta is the parameter which we are estimating, sorry, and d is the data. Okay, so what we want to estimate is probability of theta given d, and and as per Bayes theorem, it can be easily written as probability of d given theta into probability of theta divided by probability of d. Now, for the time being, you just forget about this denominator part. You just forget about probability of d, and just let's focus on the likelihood and the prior. So the likelihood is probability of d given theta. So what does it mean? It means that what, as I said, what is the likelihood of the data given the theta? So if you can see in this equation also, or the equation I have written everywhere, that is the same thing that I have used. Probability of this is the data y given x given theta. So given theta, what is the probability or likelihood of occurrence of this values or the data points? That is the likelihood. And the prior, now here comes the beauty of Bayesian. So Bayesian, so I think that many of you are aware of multicollinearity, many of you are aware of ridge and lasso regression, because those are very commonly used regression techniques in machine learning terminologies, or as a machine learning terminology. So in regression, in ridge regression or lasso regression, you know that what we do is we try to regularize the coefficient, or we try to penalize the coefficient so that it does not, so the variance does not increase, so the variance of the coefficient does not explode. And why such kind of a things happen? Because we know that if there is multicollinearity, it means that two independent variables are correlating or correlated with each other, which means it is violating the assumptions of linear regression. Or if you know that how the coefficient is, it is basically in the form of x transpose x inverse, x transpose y. So if x transpose x inverse means the determinant needs to exist. If the determinant does not exist, then it won't be estimable properly. So that is one of the problem that happens when there is multicollinearity. So what happens is, during multicollinearity, the variance of the coefficients explode. So it is very unstable. You cannot trust the coefficient. So if you have a value, if you have a coefficient, let's say someone comes up to you and says that the coefficients at y equals to 2x plus 2x1 plus 3x2. But this 2 and 3 you cannot trust, because x1 and x2 are correlated with each other, right? So in such case,
Hi,
yes,
Souradip.
yes,
Could you go through this point once again?
yeah,
Didn't get it.
sure. So okay, so so the understanding is, what happens is, if you go through the, so if you if you have gone through linear regression through and understand that how it's estimates work and how it's like, so variance of beta. Yes, yes, sure. So variance of beta is basically, it can be written as sigma square, okay, into x transpose x inverse x transpose x. Okay, so that is the form of this. So okay, now x, what is x? Now I could not here properly write it, but I guess it's clear. So it is x transpose x inverse into sigma square. So now what happens is, if there is a relationship between let's say two columns, right? If now x we know is the design matrix, right? X is the design matrix, or the feature space as we call in machine learning. It's a feature space. So if two columns are dependent, like one column is dependent on one another, so the determinant of x will be 0, right? Correct? Determinant of x will be 0. So in that case, what happens is this x transpose x inverse, if you know that how we calculate inverse, it is basically adjoined by determinant. So if determinant is very less or it tends towards 0, so that this will tend to infinity. So I think you can, I'll share some links probably at the end of the session or maybe afterwards, that where you can go and you can have an understanding that why, what happens when multicollinearity is there. So everybody knows of variance VIF, right? Variance inflation factor, if I'm not wrong. So everybody knows of that, that if it is greater than 10, then there is multicollinearity. But what truly is multicollinearity and how it affects the coefficient is like this. So what happens is this x transpose x inverse, since its determinant does not, is determinant is like indeterminate, indeterminable, or the determinant, let's say, tends to 0, so this values tends to infinity, so the variance tends to infinity. That means, what does a variance of a random variable tends to infinity mean? It means that we have a point estimate, so we get an estimate of beta, but since the variance is huge, we cannot comment on anything. We cannot say that this is huge, like this is, we are sure about that, so we are completely unsure about the beta, right? So that is what happens when there is multicollinearity. Yeah, so is it clear?
Yeah, yeah, got it, got it.
Yeah, cool, thanks. So okay, so now what I will do is, so now how does Bayesian helps? So what Bayesian does is, Bayesian induces a prior. So this prior of theta is basically, you can think of like as it is a kind of a penalty on theta, or it is kind of a bound on theta, that it is telling that somebody has a prior knowledge. So for example, somebody like, let's say, a business person, he might have a prior knowledge that this, let's say, if we are estimating some trend, so he might have a prior knowledge that this trend cannot go beyond these values, right? So he induces those prior knowledge through this equation, and Bayesian allows to induce in its equation prior information, which is the beauty of Bayesian. In any other model, you cannot give, you have to know, at least you have to give equations of the prior or something, but here at least you can give a distribution. So if somebody knows that, okay, this parameter, let's say when we are estimating A or B or C, so let's say somebody business tells us that A should vary between 0 and 2 and ideal value is 1. So you can give some prior like normal distribution, where you can at least or truncated normal, where you truncate the normal distribution into 0 and 2 with mean 1. So something of that sort you can do. So you can induce a prior, and then whatever the data is, so it will be a mixed decision. It will not be a completely data driven decision. It will be a mixed decision. So there is business decision also involved, and there is data decision also involved. So that is the best thing, right, that we can achieve. That is the most beautiful part of Bayesian, right? So now, so this is how this is the, like, the sense of Bayesian. Now I'll just try to give you a very intuitive understanding of Bayesian that is not there in many of the, that is not there in many I could not find actually, that what is the point, why we do Bayesian like this, what is the point, what we achieve. So let's say we think of that this one is the prior, so this is like a distribution plot. Okay, so let's say this red one is the prior, this green or yellowish one is the posterior, and this one is the likelihood, right? So this is how the typical scenario of regression or typical scenario of Bayesian looks like. So there are three things, as I have said. This is the likelihood, and this is the prior, and this is the posterior. Okay. So now if you see that this is the scenario of how it looks like. Now now let's say I'll give you 1 minute to think that what happens. So what happens when you take these two products? What happens when you take these two products? So what happens is, so this is like kind of a geometric average, you can think. Okay, so you can think that this is kind of a geometric average that we are doing when we are doing Bayesian. So the posterior distribution is a geometric average or a weighted average between prior and likelihood. So and any characteristic of geometric distribution or geometric not geometric distribution, when we do a geometric weighted averages, it is very sensitive to lower values in this case, right? It is very sensitive to lower values, because what happens is, if even so mostly it will be so if even one value, let's say if in this prior, so if in one value, for let's say the likelihood is very high, but if this prior is very low, for that the product will be very low, because the prior is right. So you can understand, because it is, since it's a product form, so if one value is high and one value is low also, and if let's say it is between, let's say in some range of, let's say 0.01 or something, then it will be very very low, the product. And which makes it very interesting, because what happens is it is very sensitive towards lower values. So what happens is, whenever, let's say that even the likelihood says that the value will be a bit higher. Okay, even if the likelihood says the value would be a bit higher, but let's say for that, for the prior we have given it, it is not like that, so it will decrease that, it will bound the regression, it will cut those values. So this is what the intuition, or this is the understanding of how Bayesian works. So basically what happens is, if it is basically a geometric mean type of thing that you can think of. You are taking the product, so let's say the likelihood is something, some value x1, and let's say the prior probability of for that particular point is, let's say 0.02. So though the likelihood is higher, it will reduce it, right? That is what the point is. And this is how Bayesian works. Okay, now there is just one more important step to go before we dive into the Bayesian regression part. That is a Markov chain Monte Carlo simulation. Right now, I think everybody, at least in whoever has delved into machine learning, or whoever is new also to machine learning, have definitely at least once or twice gone through in his life a term called MCMC simulation, or MCMC. So what is MCMC? MCMC is basically a Markov chain Monte Carlo simulation. Okay, so like now, to give you a very brief overview, or just to give you a introduction to the topic, what it does is, Markov chain Monte Carlo helps us in you like generating data which helps us in simulating or maybe approximating the posterior distribution. So I think you have understood that we are currently working with the posterior distribution as of now. So this is the posterior distribution which we are working with now. So what it helps is, a Markov chain Monte Carlo simulation helps is, it it generates data in such a way that we don't have to do this complex mathematics, right? So everybody is not very familiar with very complex mathematics, and everybody cannot generate, or let's say write equations to derive the distributions. So MCMC is a very like a bliss for them, because they can simulate, right? They can simulate data from a distribution, and they will get an overview of the particular distribution, which is amazing. Like when I did MCMC for the first time, I was very amused, because I thought that it won't work, because it's so simple that it tends to that it won't work. But then the question comes that we have already this probability of theta given x is this form, the Bayes theorem. We already have that. If we know the likelihood, if we know this, if we know the prior, why can't we generate the posterior? Why do we need to approximate the posterior? That is the question. It should come to everyone, right? That what is the purpose that we need to generate a posterior distribution? There is no purpose, right? So no, there is. So there is a huge purpose for that. And the purpose is, if you remember that when we used to do this type of Bayes theorem based problems, let's say in our 12th or somewhere class, so we used to have this term also, right? We used to take use of this term, probability of x. So if there is only one parameter theta, so what it would have been, in a discrete case, it would be like, if I don't know if you remember or not, so it would have been like in that scenario, x intersection theta 1 union x intersection theta 2 union x intersection theta 3 dot dot dot, how many levels of theta we have, and then we can write this in this form, right? That p of x theta, in where theta equals to theta 1 to theta p, what are the levels. And if it is a continuous case, it is basically an integration of p of x theta d theta, right? Now, so you must be saying that, okay, so this is a simple integration, right? Integration of px theta d theta is a very simple integration. Anybody can do that. So now the question is, it's not like that, because normally this is valid when we have only one parameter, that is theta. But normally we don't have one parameter. So the number of parameters will be actually how many variables you have, plus let's say an intercept, and also plus if you're estimating the variance also. So there are, let's say if there are 10 variables also, it will be, let's say 10 parameters for each variable, or basically 10 coefficients for each variable, plus one intercept, plus if you are estimating a variable, one. So 12 parameters. And then at that time, what happens is the integration increases. So with the number of parameters, this integration, it takes this form. P of x comma theta comma phi will be integration of this d theta d phi, right? And with increase in parameter, it will be integration of d theta 1, d theta 2, d theta. So it will be a completely intractable form of equation. You cannot integrate it. Like up to a point, we can also do numerical integration. We can use a lot of techniques for numerical integration, but practically speaking, this is intractable, right? So that's why statisticians or mathematicians or ML engineers, so we don't prefer to go into this depth of mathematics and try to like completely stuck up with this. So what we try to do is, we try to simulate this portion, only this top portion, okay? And if we can simulate this using this top portion only, we try to estimate this entire posterior distribution. We say that we don't need this denominator, we don't need this normalizing constant. Without that also, we can have like we can heuristically, we can slowly step by step, we can move towards our true distribution. And so this brings back to one very familiar concept, and I don't know how many of you are so familiar with gradient descent. So this is very similar to gradient descent. So when I'll be explaining the process, you will understand that it is very similar to gradient descent or stochastic gradient descent. So it is very similar to that. There also, we don't know exactly how we don't know the closed form solution. Similarly, here we don't know the closed form distribution. There we do is we take step-by-step gradients towards the optimal value. Here also we take step-by-step gradients, step-by-step steps to reach the posterior distribution, right? So that is how we do. Yes. So okay, so now let's understand how MCMC works. So okay, so Monte Carlo methods helps us in generating random variables from a given distribution. So so there are two parts, right? One is Monte Carlo and another is Markov chain. Okay, so in MCMC there are two parts. One is Monte Carlo and one is Markov chain. Okay, so guys, are you clear till now, or you have some questions? I can give 1-2 minutes. I think we are almost level. Yeah. Any questions till now?
Could you please correlate this into a real life example at the end?
Yes. So I'll show you an example, or maybe probably I'll just tell an use case where it have some implications, or where we can show some understandings that how Bayesian works in different scenarios. Okay. Okay. Cool. So now the interesting part is, so I think everybody has generated a random like we have generated different we have generated variables from different distributions, right? We have generated standard normal data, we have generated normal data. So there are if you go to sklearn, or if you go to some NumPy, so there are standard packages where you can just use np.random.random, and it will give you you specify the mean, you specify the sigma square, and it will give you the variables which follows those distribution, right? So that is pretty simple how it works. So it is, so now exactly how it works, it is difficult to tell at this point of time because there is a lot of information to it, but to give you a very brief overview of how it works is it actually takes the inverse. So it takes the cumulative probabilities. So let's say if you know the probabilities, okay, so let's say you have I'll give you an example of a discrete case. So let's say you have a probability of occurrence of, I'll give you an example of a discrete case. Let's say a probability of occurrence of an event A1 is, let's say, 0.3. Probability of occurrence of an event A2 is give you, let's say it is 0.4. And let's say probability of occurrence of an event A3, it is, let's say, 0.3, right? And we know that this is an exhaustive set. So one of the A1, A2, or A3 will definitely occur, right? Now what we do is, we you know about in uniform distribution, right? It generates uniformly whatever range you give. So what we do is we take an uniform distribution, and we mark those values. So let's say in 0 to 1, we basically separate this 0 to 1 as 0 to 0.3 as if as A, 0.3 and to 0.7 as B, and 0.7 to 1 as C. So what happens is now we generate from uniform distributions, right? Now let's say we generate a uniform distribution and it comes to 0.2. So we'll write A. Okay. Then if we generate, then again we generate from a uniform distribution and it comes to, let's say, 0.9. So it will be, sorry, A1, and it will be A3. Now again, let's say we generate and it comes A2. Then again we generate, it comes, let's say, in between 0.3 to 0.7. So again it is A2. So if you do an infinite, like very high number of samples, you will see that you can actually generate this distribution. So you are getting this ratio, right? So this is how Monte Carlo sampling works. So this is one way, and you can definitely look into different other materials, how to do that. But this is from an overview point of view, this is how it works. Now let's see that how the Monte Carlo methods helps us in generating random variables following a distribution. So we've understood that. Now it is Markov chain, right? So why Markov chain is so important? So what is Markov chain? So very simply speaking, Markov chain is a sequence of number where each number is dependent on the previous number in the sequence. So for example, if there are a sequence of number, let's say y1, y2, y3, yn, so it tells us that how y2 is related to y1, or y3 is dependent on y2, y4 is dependent on y3. So it is like a chain. So it is, you can just think of like it is a, if somebody is comfortable with graph, it is just a one directed graph. So y1 to y2, then it is y1, y2 to y3. So it is just a one directed graph, one directional graph, where each is dependent on its previous value and nothing else than that, given that, right? Now, and what is the beauty of Markov chain Monte Carlo is it is same as Monte Carlo. It's just that every time the mean of the distribution which you are generating is the previous value, right? You understand? Just try to understand this one, because if this part understanding is done, then actually one like major part of the Bayesian is done, right? So let's say from this from initially, let's say start off with theta. Okay, so we use this normal distribution with a mean which is theta t minus 1 and variance known, let's say 2 or 3. But let's say let's start off with anything. Let's start off with normal 0 comma sigma square, right? So let's say we generate a value of with normal, just write it down so that it is clear for you. 0 comma 1, right? You generate one value with that. Okay, let's say the generated value is 0.5. Okay, so you get 0.5, right? The next thing what you do is the next value that will be generated will be normal of, now you take this 0.5 as the mean of the next normal. So you do 0.5 comma 1 and generate another value. Let's say it comes out to be 0.9. Okay, then what you do is you take 0.9 comma 1 and then generate a value, right? So this is, you are using generating values from a distribution from the Monte Carlo scenario, and then you are using the Markov chain concept to every time change this parameter. So basically update this parameter. And this is very similar to gradient descent. What you do every time, if you remember, or if you know gradient descent, it is like every time you update the parameters with a better estimates, right? Yeah. And just quickly before going to the code, I'll show you one last part. I'll not go into, so there are a lot of mathematical aspects into it probably, but this session won't be enough to do that. So before going to the session, before going to the code, I'll just show you a small example. Now what happens is, if you are from statistical field, or you have read stochastic process, you know this is basically a random walk. So where your previous state determines your current state, and and there is a sigma or a variance to the movement. So you can think like a blind person is walking from one step to another step, and where his current step is just determined by his previous step, right? That is how it can be interpreted as. But if you know that if the blind person is walking like that, he can, like, it will be taking very long time to reach to the actual point. So let's say if a blind person with a stick is walking in the mountain, and he is trying to go into the top of the mountain, then it gets very difficult for him, because he doesn't know he can come down, he can go up, he doesn't know that what are the proper steps to take. So it is called a random walk. So then what comes is, there is a Metropolis Hastings algorithm. So I think even if you are not completely understanding things, just note it down and just write it down. Probably you can go through this material and you can go through the videos, then you will be very clear about how it works, and it will be definitely beneficial for you. So how Metropolis Hastings algorithm work is, it just accepts and rejects the sample. So here we are replacing these values, right? Here we are replacing the means with, so for example, when 0.5 is generated, we are taking the mean as 0.5 and generating again. If 0.9 is generated, we are taking the 0.9 and then generating again, right? So this is how we are doing. So what Metropolis Hastings does is, it gives a bound. So it gives some constraints, it gives some conditions, that if these conditions are not met, then we will not take this value. Okay. So if, let's say, if we give a condition, if the condition is like it should be greater than 0.8, or let's say it is greater than 1, so we say that if the conditions are not met, then we'll reject these values, we'll not take these values. So for example, in this case, the let's say the threshold is, it should be greater than 0.6. So this is the condition that Metropolis Hastings has given. So now you see that value came out to be 0.5. So you will not accept this value. You will again generate with 1, 0 and 1. So you will not update this value. You will again generate with 0 and 1. Let's say the value come out to be 0.4. So you again reject it. You keep it 0, and you keep it until you get an acceptance. So once you have 0.7 that is greater than 0.6, and then you accept this new value, and this is converted to mean. So this is, you can think of like when the old man with a stick, blind man with a stick, was walking in the mountain. So somebody is telling him that now, let's say he's taking a step. Now somebody is guiding him, telling him that, okay, is that step wrong or right? So if that step is wrong, he will stay at his current position only. If his step is wrong, he will stay in his current position only, and if his step is right, he will move on. So this is exactly how gradient descent works, and this is exactly how we update our posterior distribution for Bayesian linear regression. Now there are a lot of mathematics that we do. There is Gibbs sampling and a lot of other things that we do, but I think it will be better if I go through the code once, right? So this is again a very simple code. I have generated data, so that it is not like I've taken some data from some competition or something, so that it is very difficult to understand. So now let's say I'll tell you the data generation step. So for our case, n equals to 100, so we are generating 100 samples, so we have 100 observations. Okay, this a is the true value of, so the equation is ax plus b. So a is the slope. Okay, so you know the true value of the slope is 6. Okay, and you know the true value of the intercept is 2. Okay, if there's a straight line, there are two things, right? Slope and intercept. So intercept is 2, and let's say the this slope is 6. So you know that, because I want to check that whether using Bayesian regression I get this kind of a same intuition or not, right? So this is how it works. So this is the slope and this is the intercept. Now what I do is I simply generate np.linspace 0, 1 to 100. So what it does is it gives me, if you see this, if I just run this quickly, and if you just see, what it will do is it will give me an uniformly distributed, like it will be uniformly distributed or uniformly divided values of x between 0 and 1, and it will give me 100 values because n is 100. And then I generate the value of y, where y equals to ax plus b. So it will multiply a into this x plus b, and then I give a random error to it. Okay, so in this np.random.random, it will generate a standard normal variable. So the variance of the error will be 1. So basically what I'm doing is, if you remember that this equation which I had written initially, so what I'm doing is I am giving as I have given a value to a, I have given a value to b, and I have given this sigma square as 1. Okay, and I want to estimate that how good my Bayesian linear regression is doing. Okay, yes. Now what I do is, let's say I do 1,000 iterations. Okay, now these are the packages that needs to be installed and imported. I think most of you who are familiar with Python and notebooks, I think here they will be perfectly familiar. So this is the package for Bayesian. Okay, this is the main package for Bayesian. So this is import PyMC3 as PM. So if you do that, you will get the, so this PyMC3 is, there is a, like, it's very good for this kind of simulations, sampling, different sampling, and testing different experiments. And once you install that, so what you have to do is, you have to just run this PM model. You generate this is the prior. Okay, so you tell us that what is the prior that you want to use on. So they ask you that what is the prior that you want to use on these two parameters. So there are two coefficients, right, a and b. So they ask us that what is the prior that you want to give. So a is this one, and b is this one. So we tell that, okay, I want to give prior of normal distribution on a and normal distribution on b, right? And then what I do is I also generate a sigma value using an uniform distribution. So these are the priors. Okay, just so that you don't get confused, as I have told you already, that there will be two components of when you are estimating the posterior. So the two components will be, one will be a prior and one will be a likelihood. Okay, so the likelihood is the one that MLE and everything that I had explained. So that likelihood is that, and this is the prior. Where, so here you can actually give your business sense. So if your manager says that okay, I want this a value, I know that this trend can vary between 5 to 10, so you can generate a uniform giving 5 to 10 as a prior. Okay, cool. So now this is the sigma, so you give a prior on sigma also, and then this is the equation. You specify to the PyMC3 that this is our equation. Okay, and the likelihood. So likelihood, as I said, that likelihood follows a normal distribution. Basically y follows normal distribution, and likelihood will be product of them, as I have shown you in the blog writing also. So it will be pm dot normal. This is the y. Okay, the mean is this y estimation or y estimated, which is ax plus b, if you remember. Mean is this one, and variance is sigma square, and variance is sigma, which we are generating, basically, truly speaking. Okay, so now you have this likelihood. Okay, you have these priors, and you have this maximum a posteriori, which I had mentioned. So maximum a posteriori is basically like likelihood. In likelihood, you get a point estimate of the maximum likelihood estimate as a maximum likelihood estimate. For posteriori, you get a maximum a posteriori value. So for example, instead of the finding the maximum value in the likelihood one, you find the maximum value in the posterior distribution. So now you just do start equals to this. You tell the steps, that at what step it needs to be done. Now it performs something called a Hamiltonian MCMC. So I don't want to go into Hamiltonian MCMC because it is derived from the concept of statistical mechanics, and it will be exceptionally tough if I explain. But let's say you can use Metropolis Hastings also, so that is also similar, so nothing wrong will happen. So this is how Metropolis Hastings you can use. And then what you do is you pm dot sample this n iter, and this will tell you do the process that we said. So it will sample from the posterior distribution, basically from this product of the likelihood and this prior. Okay, as I have shown here. So is basically it will yes, in this case, so it will basically generate from this posterior distribution step by step. And now if you do this trace plot, you will get that this beautiful plots. And the very interesting and best part of it is, if you see the estimates of A, it is almost 6, right? And if you see what we have taken, it is 6. Similarly, if you see the estimates of B, it is around 1.7 to 2, basically 1.9 or something. So if you see, B is 2, right? So you can see that this is such a beautiful thing. And the most interesting part of it is it gives a distributional analysis of these parameters, which we don't get into in when we are doing simple linear regression. We don't get such kind of a distributional understanding or distribution analysis. Okay, so this is one part of it. Now what you might tell that this is very top level package. So for people who don't want to go into too much mathematics, and who are like more they want to experiment and run various experiments and understand the intuition, for them this package is the best thing, PyMC. But for people who wants to have a deep understanding of mathematics and I want to see that how it works, so I have also done this Bayesian linear regression using Gibbs sampling, which is probably will be in the blog also, so you can just see. So I will give you just a quick understanding because we have less time left. So a quick understanding of how Gibbs sampling works is, so if there are 3 parameters, okay, if there are 3 parameters, let's say A, B, and C, so it tries to find the conditionals. Okay, it tries to find probability of A given B, C, and the other things, then B given C, A, and other things, and then let's say sigma square given A. So whatever parameters we need to estimate, let's say if there are 3 parameters that we need to estimate, A, B, and C, so it tries out to find out conditionally one after the other. So intuitively what it does is, it first, let's say, assume some value of the other. Let's say there are 3 parameters, A, B, and C. Okay, so first what it does is it takes some random value of B and C, and then it tries to find out what is the probability of A given B and C, and also Y and X. So it tries to find out the probability of A. Basically this is a kind of a conditional distribution of A, posterior A, and then it generates some random value of A from that posterior distribution. So then what it does, it puts that value in the posterior distribution of B and C, and like that it keeps on updating and iterating. So if you see the codes, if you see this part of the code, it will be very clear that what happens. So first it will update. So see, first it updates C. Okay, then it puts that value of C when updating B, and then it puts the value of C and B when updating T, and it does that in a iteration. So it does that several times. So and then if we do that several times, what happens is this kind of a plot you will get. And I have ran that same in understanding in this for the same data also, and you will get this estimate. So if you can see that this is the slope is actually centering around 6, the precision is centering around 1, and the intercept is centering around 2, which were the values basically taken. The advantage is you get the distribution, you can calculate mean thing, anything. Okay, and another point I think that I should mention is the burnout period. So we always try to separate the burnout period from our distribution, because that burnout or burn-in period, that is basically the starting point. And we know that the starting point, simulations, people who have worked in computer science or ML or any stat field, they know that during the starting point of the simulations are basically bogus value results. So they will not get into meaningful results. So they'll try to generate bogus results. So the starting points we try to avoid. So you can see that we have avoided this starting point using this. So if I take this 500 is to 14,000, that means that the top 500 values I am not taking, and because those are that is it's precisely called burn-in period in terms of in Bayesian language. And so what we do is we simply avoid those, ignore those, and then we can see that this is the beautiful distribution that you get. right? And I have also explained this using Metropolis Hastings one, that how you can do Bayesian linear regression using Metropolis Hastings. So that is in this notebook. Probably I think time is not there much to go and explain, but this is also pretty simple. So if I just look into the code quickly once, what it does is it finds out the sigma square estimate using a sigma square distribution, assuming a prior distribution of sigma square, and finding the posterior, and then similar method. So I think all the Bayesian works in this similar method, where you for multiple variables you try to find their conditional posteriors and try each and update each and one other with different forms of simulations. So that simulation can be through Gibbs sampling, Metropolis, or Hamiltonian, but the basis is Markov Chain, Monte Carlo. So it's an MCMC simulation practically. Okay, so this is one major thing of Bayesian. So you get this kind of estimates, and that actually helps, right? Because if you study deep learning, and if you go through various advanced technologies, you will understand that just giving a point estimate, just giving a value, it helps. Like, business is not happy with that. Business is never happy. Business wants to know that what is the uncertainty, right? What is the uncertainty in a particular value, or what is the uncertainty in our coefficient. So Bayesian actually provides you with this uncertainty. And yeah, so I think this is more or less, I have to 1:15, I have exceeded 1 minute. So this is a very complex topic, and it needs several much time, but at least you know the terminologies now. You can just go through this blog, you can go through these materials, and you can have a good understanding of what is happening. And I'll definitely say everybody who is starting off to understand things from mathematically as well as implementation wise, so that you have the true depth in understanding. And just to just since this picture came in front of me, so as I said, right, we'll update one parameter, and then we'll update the second, we'll update the third, we'll update the second, right? Like that it goes. So it goes in this kind of a rectangular path. So though it takes time, but it actually generates this posterior very efficiently. Yes, I think this is for me. I think now you can go ahead with the questions.
Yeah, so like I am
Yeah.
sending you a few questions on WhatsApp,
Okay.
because it's quite like, there are a lot of things going on in the chat window, right?
Yes.
So I will
Yes.
send you the WhatsApp, and you can just see from there. Right, I have just mentioned the name also, like name and the time. You can just see.
Sure, sure. So I am just going through that. Okay, so give me 1 minute. Yeah. Is MLE used for point estimates? Yeah, it's correct. So whatever you have said is very right. So MLE estimates are generally point estimates, where you will get a value. So you will get a single value when you do. So for example, if you have an expression, let's say the expression will be in the form of a mean. So let's say 2 mu or some 3 mu. If you differentiate it with respect to mu, you will get a particular value, right? So MLE is a value. Okay, correct. Now the next question is, so you use this to calculate the maximum likelihood that certain data points will overlap. Then you check the accuracy by what data was later actually captured. Um so it's like, again, I'll just explain you. I think I'm not very clear with this question, that what you mean by the overlap and all. But what I mean is, so what I mean is, it will be kind of it is basically, that let's say you have a box. Okay, now you have a box and you have many red and blue balls. Now what you know is, you don't know that the exact distribution of the balls over there. So what you do is, what a standard person will do is, it will pick different balls, right? And it will try to, based on picking multiple balls, it will try to comment, right, that what is the best estimate of the ratio of between red and blue balls. So similarly this happens. We give a small sample set to our, let's say, the statistician or the engineer, and then he knows that these are the standard parameters of a normal distribution, and he sees that what is the best parameter that can generate those points, right? Yeah. Then is MLE used only in logistic regression? No, no. So MLE is used in logistic regression also. The example I showed is linear regression, right? So MLE is also used in linear regression, and wherever you have to estimate a distribution and you have the likelihood, you can always differentiate it and find it the MLE. Okay. Can you provide list of books which we can use for Bayesian regression? See, so there are one very good book, and one person which I am a big fan of is Professor Gelman. So he is a god in this field. So I feel that you should definitely refer and see his books. And then other than that, there is David Barber from UCL. So he also has a very good amount of knowledge in Bayesian, and his book is also very good. So it is like Bayesian and also Bayesian NLP and Bayesian Deep. Yeah. Then what is that? Please cite some use cases where this has been used. Okay, so there are several use cases. Okay, so probably what one use case comes to my mind is, let's say, different types of. So let's say when you are there is an accident. Okay, so you are counting that. So when let's say, or there is some kind of a default loan default. Okay, so in cases where there is a default, or there is something like that, where when there is a critical binary class problem, so you try to estimate the parameters, but then the business will ask you that what is happening to this, why, because with time there can be certain things that changes, right? So what is happening to these estimates, why it is changing? So you cannot tell this if you are using point estimates for MLE. So you have to use Bayesian in that cases, so that you can have you can understand how the distribution of the estimates is changing rather than the point. Why did we ignore the normalizing parameter? We okay, so as I said, that we are not ignoring the we are definitely not ignoring the normalizing parameters. What we are trying to do in this case is the normalizing parameters, if you have seen in my talk, it is like intractable, because there are a lot of integrals that we have to do, and it is practically intractable. So for such cases, what we do is we try to just take the top part, that is the likelihood into prior, and simulate data which actually. So okay, let me give you a very simple example. So let's say if you have, so if I have as I've shown you, right? So if I have this thing, right? If you can see this, clearly. Oh, I think I'm not sharing. So okay, so what I have told you, right, that we have this probability of d given the data given theta into probability of theta. So the probability of theta is the prior, and probability of data given theta is the likelihood. So likelihood into prior at time point t, and likelihood into prior at time point t plus 1. If you take this ratio, then the denominator gets cancelled, right? So then we don't need the denominator. We utilize this ratio in generating. So that is what Metropolis Hastings does. Yes. Okay, can you help me understand more of the closed form? Yeah, so that is basically Gibbs sampling. I will share you one link immediately in the chat box, so that you can go through these links, and you will understand that how the if the closed form is there, how it works. So that will help you in understanding that if closed form is there, how it normally works. So just see this link, you understand that how a conditional closed form works for this posterior. Okay. Can we implement Gibbs sampler using PyMC3? Yes, you can implement that. So you can implement Gibbs sampler using PyMC3 easily, and that will be quite easily implementable. So you just type Gibbs sampler using PyMC3 Python, you will get that links. Do we have a recorded version of this session? I could not get the link. How gradient descent pitches in here. Okay, so see what we are trying to do is we are trying to ultimately estimate our parameter. Okay, we are trying to estimate our parameter from the posterior distribution, right? Or basically we are trying to get the posterior distribution of our parameters now. And but that is unknown to us. We don't know the exact function. We cannot differentiate the function, right? So, and what happens in gradient descent also, we know a curvature, we know a path, but we don't know the exact differential or the closed form solution of the path. So what we do is we move step by step in gradient descent also, as per the gradients. So here also in gradient descent we move in the direction of negative gradients, or maybe del j del theta to be simple. Here we move in the direction, here while we move, we have an acceptance sampling. So some person, you can think that he tells us whether to move in that direction or not. If it is not to move in the direction, we stay where we are. Okay, do we have, okay, right, is list any pros and cons of Bayesian? Okay, so one so pros of Bayesian I have told, right, that it reduces overfitting. So somebody had asked that why does it have any overfitting or not. So as I have said that in during overfitting, the coefficients are unstable, the variance of the coefficients are not very stable. But when you will do this kind of a problem, that Bayesian, so there you will get the variance, the posterior distribution, that will be very stable and that will be robust. So that is one major advantage. And con is definitely it is a bit slow. It won't give probably that much accuracy, because since the underlying distribution is linear regression, so let's say it cannot give you the accuracy achieved by very complex boosting models. But I have seen in various cases, and especially in Kaggle, there are few grandmasters who use Bayesian a lot, and I love their kernels. Probably you can just see. I'll share some names later, but there are a lot of Kaggle grandmasters and masters who use Bayesian a lot, and that is like, and their kernels are a treat to watch. What percent of the total samples we take as a burnout period? So that is a good thing. So that is basically kind of a, it is not a hard and fast thing. It is basically kind of relative. If you are generating, let's say 1 million samples, you can take the top 1,000, or you can take out the top 20,000. But if let's say if you are generating, let's say if you are generating some 500 samples, then you cannot remove top 1,000, right? Or maybe top 100 also, right? You have to reduce top 50. So it depends kind of that what is your computation power, how much you can generate and all. Okay, is there anything equivalent like the assumption of linear regression? So assumption as in there is, so those priors, right, those priors that I have taken, so the priors, the distribution of the priors, those are all assumptions, right? So those are basically practically those are all assumptions of our Bayesian. We have to assume a particular prior, and that comes from business knowledge. So that is like, we assume that the prior should be like this, we assume that the likelihood distribution is normal. So these are the assumptions that is still there. Okay, and if we do more burn more data, will it affect the outcome? It should not ideally affect the outcome, because if even if you do more, so what happens is after a particular time period of burn in or burn out period, it actually converges to the true distribution. uh, and thank you, Sparsh. It was very complex, and I tried my best. Yeah, so what happens is if you do more burn-in, so what happens is after a point of time, it will converge to the true distribution. So even after a particular period of time, I'll tell you. So after a particular period of time, it will converge to the true distribution. So it doesn't matter if you take burn-in of 1 lakh or 1 million. After that, there will be convergence. So you will get the true distribution after 500 burn-ins only, or 1,000 burn-ins only. You don't have to do for long. Now, but again, the problem is in complex scenarios. Let's say if the posterior is very complex or something, then more number of let's say we have to burn in more, because the parameters will take more time to reach to the true distribution. Okay, so then there was another question called how to get started with Kaggle competitions. So how to get started with Kaggle competitions? There are many blogs. You start with like you read those. In one of my previous sessions also, I have explained that how to get started with machine learning and how to do data science. So one of my previous talks was on that. You can have that. You can see the talk. That was a part of, I think, Google developers talk at VIT. So you can do that. So there are a lot of, yeah, as Arun said, there are a lot of Kaggle masters and grandmasters. So you can definitely ask them, and they'll, yeah. Is that uploaded on YouTube? That is uploaded on YouTube. Absolutely, that is uploaded on YouTube, and you can get that. So there was another question which was asked, was that how to decide the prior distributions. So how to decide the prior distribution is based on business sense, right? So or you talk to business that, okay, if this is a trend, let's say you are selling certain items, and let's say you want to see that how the sale price varies with let's say the number. So if there are, let's say, 10 items in a shelf, and there are 100 items in a shelf. So if you increase or decrease the number, how does the sales vary? So let's say you want to find that. So you can always go and ask the business, right, that what is the ideal coefficient that you expect, how much should that happen? So he'll give you a prior. So you make that in a distributional format, and then you do your analysis. So this is like a most beautiful part of Bayesian, that it helps you in incorporating the business knowledge also, right? Yeah. Does companies like Walmart and Amazon expect knowledge of Bayesian regression in a depth matter? So I don't know that do they expect that or not. But I feel that if generally companies expect that whatever you are learning, whatever you are doing, you should be very good at that. You should be very confident, and you should like, there are, see, the problem is there are now lots of packages, and there are some packages which are not right also. So you have to understand the mathematics, and you have to understand at least the intuition behind it. Without that, you should not go ahead and do. Yes, I think this is all. I think,
So thank you so much, Sauradip bhaiya. Thank you
yeah.
so much.
Hey, on Akash this
So
side. I have one question.
Mm.
yeah,
Hi, Sardeep. So I
Hi.
had one question. We
Mhm.
were talking about Markov Chain Monte Carlo simulation.
Yes, yes, yes.
We were also talking about how to we will
Mm.
for the number of simulation iterations, we
Mm.
will sort of
Yeah.
converge towards the
The true
true
posterior.
posterior distribution.
Yes,
So what I can think of right now is how to determine that convergence, like
yes,
how to decide whether we have
yes.
converged or not. One of the ways I can think
Mm.
of is autocorrelations.
Mm.
But can you maybe give some more example other than
Mm.
autocorrelation,
Mm.
or also confirm that autocorrelation is one of the way to
Yes.
can it be one of the way to determine the convergence?
So I think that autocorrelation is definitely, so autocorrelation, it is, I think it's a big term, but I feel that yes, you can always check that how your values are varying, like, right? If you have, let's say, generated, let's say, some five, let's say you have done a 1 lakh iteration. Now you want to understand that what like whether there is kind of, it has already converged or not, right? First is like, you, once you see the plot, you will understand that after a point of time, it hardly moves. It actually oscillates beyond a certain value, and that is a kind of very, the oscillation is also not huge, like it's not a, like a spike. It is a, so what you can do is autocorrelation will help you, because you will get to know that whether this, how the values are dependent on each other, right? So that kind of an intuition will get. But uh, how to get the convergence, normally we do from the plots only, right? So we can see the plots, and we give them, let's say, one million iterations on 1 lakh or whatever it is. But the good part of Bayesian is, what I'll tell you is, it needs minimal data to converge, and that is the best part of it. Yeah.
Okay, awesome. Thank you so much.
Yeah.
yeah. So before moving, the person who talked now, Akash bhaiya, he's a speaker for June's first meetup, right?
Oh, wow. Yeah.
Yeah.
Like,
So I can give you, guys, if you have one, some people were asking practical application of this thing. I actually worked on this Markov Chain Monte Carlo simulation once in previously. So basically, one of the practical examples I can give, which I worked on, it was related to the pharma field. Pharma field, by that I mean that let's say if a drug trial starts. Whenever a new drug comes into the market, it first goes through a trial. Okay. And by trial, I mean, once the trial is complete, then the concerned authorities approve that drug or disapprove that drug based on the results of those trials. So what companies do, let's say a drug for cancer has come up, or say, let's say, drug for COVID has come up. So COVID is sort of a viral disease. So generally company, what it does, they sort of allocate few hospitals to conduct those trials. And now how to decide which hospital to choose? So they look at the historical data, like on in this particular hospital, we had sort of, let's say, many people coming for virals, or many or whenever in past, if there is a trial related to viral infections, many people participated there. So companies generally tend to activate those sites for the new drug for the viral infection. So basically, patient this thing is this whole concept is known as patient enrollment. A patient enrollment into a trial, and always a patient enrollment also follows some particular distribution. And if a new study, if a new drug comes into the market, we do not know what would be the trend of that patient enrollment for that new drug. So I use this Markov Chain Monte Carlo simulation to sort of estimate the distribution, the posterior distribution, as Souradip very beautifully
Yes.
explained, posterior distribution, to give a sense to the sort of to our clients or whoever we are providing the services to our clients, that this is the posterior distribution it will be following based on the past data, maybe past data of similar drugs related to viral infection. So this is one of the practical examples you could think of, basically looking on similar studies, or maybe if you have very less data and if you want to increase the data, we can use this simulation technique, Markov Chain Monte Carlo. I hope this helped.
Yeah, I think Akash, that is a beautiful example that you have given. Actually, that is very relevant example. And just to add on to that, there is certain other thing I'll just add, that when there are hierarchical structures in the data, for example, if we know that there is, let's say for example, if you are classifying cats, and out of those cats there is a particular species of cat. So if there are some hierarchical structure in the data, then also you can use Bayesian prior posterior this theory very efficiently, so that it will help a lot.
Yes, definitely.
And then I think there are some questions around, will there be a random generation that is different from other points? Okay, so the idea of random generation is that only that it will generate various type of data, and it will generate. So if you have a distribution, it will try to generate more number of points which are having a high likelihood or high probability of occurrence, and less number of points, but it will definitely generate lot of new data points which replicates the distribution. Regression may generate. Okay, so quickly summarization. So summarization is like simple summarization will be that in simple linear regression we have a lot of estimates from MLE estimates, or which are point estimates, which are good, but we don't are sure, or like we don't know the exact confidence, and we don't know the distribution of those estimates, which can lead to a lot of problems. One is interpretability, one is overfitting. So if there is overfitting, we won't get any indication, and this kind of problems can be there, and it is not very robust, but and it needs a lot of